This time, I'm going to talk about how to build the trinomial tree for Black Karasinski model in Python. About 1 year ago, I published a video, Black Karasinski model and calibration in Python, in my YouTube channel. If you haven't watched that video, you are welcome to watch that video as well. One of the viewers asked me a question: how can we build a trinomial tree for Black Karasinski model? In this video, I'm going to answer this question. The Black Karasinski model is a framework used in finance to describe the behavior of interest rates over time. It's categorized as a one-factor short rate model and the extension of the Vasicek model. Unlike simpler interest rate models, the Black Karasinski model incorporates mean reversion and stochastic volatility, allowing for a more realistic representation of interest rate movements. This model is particularly valuable in valuing interest rate derivatives and pricing fixed income securities by providing a structured approach to understanding and predicting interest rate dynamics. This is the formula of original Black Karasinski model. And there are many enhancements of Black Karasinski model. In this video, when I built my model, I used this enhanced Black Karasinski model from this professor in National Taiwan University. You can see in this formula, this mean reverting model depends on time through kappa, theta, and sigma. And the kappa here is the speed of mean reversion. And the sigma is the short rate volatility. And theta is a long-term mean. Means that's the mean reversion level. And Karasinski model has many key features. I talked about those key features in my previous video already, so I will not repeat them again here. If you go to this website, you can find this trinomial tree building methodology on Wikipedia. But under this trinomial method, the underlying stock price is modeled as a recombining tree. But now we are talking about interest rate movement. So if you take a look at the formula, this Q is dividend yield. Because we are talking about interest rate movement, we don't have any dividend concept here. You see, Q is its corresponding dividend yield. And also, there are certain restrictions for this one. Because if you have sigma too small, you will get this PU and PD is greater than 1. But you know, PU is the probability of going up, PD is probability of going down, and PM is probability go to the middle. So they should all be between 0 and 1. So there are certain limitations for this sigma as well. of course, you have to consider the relationship between sigma and r in order to satisfy this equation. These are the formula I got from that website I just showed you. This R up means how much the interest rate will go up. R down means how much the interest rate will go down. And P up means probability of going up. P down means probability of going down. P middle means the probability the rate will go flat. And so here you can see this is the formula, and this is the formula for the probability. Because now we are talking about interest rate from the starting point. For example, if we have interest rate 0.05, if you use this formula directly, the interest rate will go down easily to negative territory. So in order to prevent that, I add another factor called up-down factor. It's about 0.001. So the interest rate won't go to negative easily. And now let's see how can we build this trinomial tree. First, at the beginning, we only have one data point, point A. And then, first step, it will go down to here, and then the probability of going here is 100%, because there's no other way to reach this data point. And D will be the rate goes down times up-down factor. Similarly, when it goes straight here, also the probability is 100%. Also goes up has 100% when it reaches data point D. When we build this trinomial tree for Black Karasinski model, only difference is when interest rates go to C from A, the interest rate will change based on the formula of Black Karasinski model. It's not the same. And now let's see how can we build the next level of the tree. From C, how can we reach G? Because when we consider G, it has three possibilities. You can reach G from point B or C or D. Now we have to consider the probability of going up, means this one. You see, I use red color for up. And also the rate goes up is R up here. You have to consider this one. The green arrows means it goes into the middle. So in this case, from data C to data G, you also have to consider the probability of goes to the middle. And the rate will change based on the formula of Karasinski model. And similarly, for D, you have to consider the probability goes down, and probability goes down is here, and the rate goes down is here. And then you sum all three up, we'll get this data point G's value. Okay, now let's consider this E and F. So for E, this is easy because there's only one way you can get there. This is at the left side of the tree. So you have 100% probability to get E from B, and the rate will go down. So you just consider this R down. That's it. But for F, there are two ways you can get there. One is from B, one is from C. So for F, you have to consider the probability of go to the middle and probability of goes down. And please remember, these two possibilities should sum up to 1 because there are no possibility for other data point to goes up. And then you will use those two paths to calculate the value of data point F. So for data point I, this is easy to calculate because there's only one way to get there. You only consider the rate goes up from data point D. And for H, similarly, you can calculate the value from rate goes to the middle and rate goes up from data point C. Again, you have to sum up those two possibilities to get 1 because there are only two ways to get to the H. So to summarize how do we build the tree, you have to consider either this data point is on the left side of the tree or is on the right side of the tree, or it's in the middle of the tree. And for the data point, if it's on the left side, you only consider the next data point goes to the middle or goes down. And for the right side of the tree, you only consider the data point go to the middle or goes up. And for the data point in the middle, that's quite simple. You only consider the next data point go to the middle. Why you don't consider goes up and goes down? Because those data points will be calculated by other data nodes. For example, the F will be calculated by B, and data point H will be calculated by data point D. So from C, you don't have to consider those data points. You only calculate data point G, that's it. But on the left side, you have to calculate 2. From B, you have to calculate E and F. From data point D, you have to calculate H and I. Okay, now we know how can we build this trinomial tree for our Black Karasinski model. Now let's go to Python to see how I implemented that trinomial tree. Okay, this is the Python model I wrote in order to implement this trinomial tree for Black Karasinski model. You can see I built trinomial tree here, and I can draw the tree, and here I sum up all the value from certain level. For example, for this level, I sum up all the interest rate for all those notes and take average to consider as the real model interest rate for this level, for this step. For example, if this is step 0, step 1, step 2, for step 2, the interest rate, I will consider the average of all the data nodes will be the final interest rate for this step. I will calculate average and draw it, and here I have time horizon 1, and for the level I put 5 here because if there are so many you can't see it, it's too many steps. Of course you can increase this value to like 252 or something as you like. And the interest rate will start from 0.05. Theta is the mean reversion level. I put 0.06 here. For kappa, it's a reversion speed. I put 2.8 here. For sigma, it's a volatility. I put 0.02 here. And if I put 0 to this Wiener process, you can see here in the formula, Wiener is here. You can see I use Wiener here. If this is true, I will consider this random factor. In other words, I will consider sigma. And if we add a random process here, sometimes it's very difficult for us to validate our model. So if I turn it off, I put 0 here, I will not consider this random factor. If we go back to this formula, that means if I consider Wiener, I will consider this item. Otherwise, I will ignore this item. You can see we only consider this first item in the formula. This is what I explained with the slide. You see, if it's level 0, the first node, I will calculate the next level like this. Otherwise, if it's on the right side of the tree, I will calculate the tree node in the middle and when it goes up. And if it's on the left side of the tree, I will calculate the rate goes down and also the rate goes into the middle. Otherwise, I will only consider the rate go to the middle. Okay, now let's run our model. You can see, first time I put this Wiener process at 0, so we don't consider this Wiener process. It will start from the initial interest rate 0.05, and you see over time it will go to 0.06, which is this theta, this mean reversion level. If you check the tree, you can see from the first data node the interest rate is 0.05, and if it goes to the middle, it will become 0.0556. This is because we are using Black Karasinski model, so the interest rate will change a little bit, and then the rate will go up to 0.0566, and if it goes down, it will become 0.0546. And you can trace the tree to see, and if it keeps going down, and it will become something like this, and this side will keep goes up until it reaches 0.0616, and I will take the average, and you can see the average interest rate will go like this. It turned to this mean reversion level 0.06. Okay, if we change the kappa, for example, we don't put 2.8 here, we put 0.8 here. You can see over time it will change to last value 0.056, not 0.06, because now it's a slower approaching to this final mean reversion level. If we put kappa as 5.8, we run it, you can see it will reach and even goes too much for this mean reversion, and then it remain around 0.06. Okay, let's put it back as 2.8. How about we put Wiener process in? If we put 1 here, you can see it shows something like this, because with those data points it's hard to validate our model. If you run it again, you see it shows like this. Basically it's trying to get to this mean reversion level 0.06, but will bounce around this mean reversion level. You can see it shows something like this, something like this. Okay, how about we increase this n? If we put like 25 here, because now we only have like 1, 2, 3, 4, 5, right? If we put 25, it will take longer time. You can see it shows something like this. Basically, it's so many data points. I didn't put label here because even I put there, it's hard to read, and it shows something like this. And if you run it again, you can see it shows something like this. You can see this interest rate is trying to get to this 0.06, which we specified with theta, and it goes something like this. I will upload this model, this Python code, to my GitHub. You can download it and change the parameters and try it by yourself. In this model, I put theta, kappa, and sigma as constant because I tried if I change the value, for example sigma, because the limitation of this trinomial tree formula, if sigma is too small, and sometimes it can't even build this trinomial tree. So if you have better idea to put those theta or kappa or sigma as a time-dependent variable, you can also provide your code or your idea in the comment area or in my GitHub. This is how I built trinomial tree for Black Karasinski model in Python. Please comment, like, and subscribe to my YouTube channel. Thank you.